Okay. So here, there's no way that we can rewrite this using partial fractions or anything else. We can't do anything with it. So it's not going to be this. So we've basically run through everything we know at this point. So now we say, okay, maybe the integral test, all right? Maybe the integral test. So this is the series we're going to work on. I'm going to show it to you first to try and convince you of why the integral test works. All right, so let's look at the animation of it. So here we go. So I've got a lot of stuff. I got a lot of stuff here for you to look at. On the left-hand side here in the green box, what you're seeing here, and I need to make these points a little bit bigger so you can see them. Okay. So what you're seeing here is the black dots are the sequence of points, right? The sequence, not the series, the sequence. So when you plug in 1, you get this. When you plug in 2, you get this, and I can have more points here. And then the blue curve is the sequence rewritten as a function of x. So instead of just being the dots, it's everything in between the dots. And so if you just look at each of these points, the black dots, and you imagine that there's a rectangle that has a width of 1, okay, so it's 1 unit wide, then would you agree that the area of this first little dotted rectangle here would be 1, that's how wide it is, times how tall it is, which would be the sequence, the value of the sequence, right? So that little gray area is basically equal to the height of this dot. That's the area. And then if I do that with the next point, I get another rectangle, another rectangle, another rectangle. Then what the integral test says is that if you want to look at the sum of all of these rectangles, right, that would be the sum of the series. That's this right here. Then that should have something to do with the area underneath that blue curve. So if I just keep on dragging this out to the right, you can hopefully see it's slowing my computer down. But do y'all see that? That's a typo. That should say negative x. It should say negative x right there. I don't want to change it because it's going to mess. I'm going to have to redo the whole thing. This should be x e to the negative x to match up with n e to the negative n, okay? But the important thing is to see that the area underneath this curve looks like it's converging. As I continue to go out further and further, again, it's slowing my computer down, you can kind of see that this number is not changing, right? It's getting closer, it's converging to something. And so is the sum, right? So is the actual sum of the sequence points. So it looks like if the area converges, so does the series itself. And that's what the integral test is basically doing. Does that make sense? That if the area under the curve converges, then so should the area of all those rectangles together? Okay. Now, go ahead.
No, you're good.
Okay. Now, the test works the other way around too. So it says that if the area diverges, that the series should diverge, and I have an animation of that. This is a different function. This is actually the series, just so you know, this is the series 1 over n, which we know is harmonic, right? This is harmonic.
Right.
That should diverge. But you can see here that as I start going out to the right, these areas, right? I'm looking at those and I'm comparing to the area under this curve. And if I go out further, watch what happens to this area. This area keeps on growing. Now I have to go out pretty far. And again, I'm slowing my computer down here, but I can just keep going. See how it's just not flattening out? It just keeps on getting bigger and bigger the further I go. So the area under 1 over x diverges, and so does the series, right? 1 over n. So that's basically how the integral works. It works in both cases. You got convergence of the area, you got convergence of the series, you got divergence of the area, you got divergence of the series. Okay? All right, so let's get back to this. Let's get back to this now.
Professor, are these like different type of functions? Like for example, like that one's 1 over n and the other one's 1 over x. But we know that 1 over x is a type of function.
Mm-hmm.
So it's 1 over n.
Well, what the integral test says is that we are going to convert our sequence over to a function of x, right? Where did my... So they're not the same in this. I'm not quite sure I understand your question. They're not the same. Like one of them is a sequence, right, which is only defined on the natural numbers, right, 1, 2, 3, 4, and the other one is a function which we are defining on the entire interval 1 to infinity.
Okay.
So they're not exactly the same. They have different domains.
Okay.
Let's do this example. I think once I do, 2 examples, I think it'll start to hopefully become clear. All right, so here we go. We come back to this. I'm going to erase this because we don't really need that. And I'll just rewrite that. So n over e to the n. Okay, we know that none of these worked. So the next thing that we would want to do is take a look at this and convert it to a function of x. So I'm going to convert that to f of x equals x over e to the x. And I only want to look at that on 1 to infinity. Now, the reason I'm only looking 1 to infinity is because the sequence is only defined on the numbers from 1 to infinity, right? So we only need to look at this function to the right of 1, right? That's the only thing we need to consider. And now comes the tedious part. We have to show it's continuous, positive, decreasing, and integrable. So what I always tell students with the integral test is before you go starting to figure out whether or not these 4 things are true, just ask yourself, do you feel like integrating this? Because you're going to have to integrate it at some point. Like, do you feel comfortable integrating it? If you don't feel comfortable integrating it, then the integral test is probably not for you in this case, right? Now, I actually don't feel too bad about integrating this. What do you think? If I rewrote this as x e to the negative x, could you integrate that? If so, how?
By parts.
Yeah, you just do that integration by parts, right? Good. So, that's the first thing I always look at. Do I feel, can I integrate it? Yeah, so I feel like I can integrate it. It's integrable. So back up here, the 4 things we had to check. It is integrable. It is something I should be able to integrate, all right? Now, is it continuous? Is this a continuous function? That just means, are there any points in our interval where this function would be undefined? So there's nothing I can plug in, right? I mean, no matter what, I'm never going to get division by 0. E to any power is always positive. So this is a well-defined function. It has no discontinuities. We should be good with this. That's just like a visual inspection, really. So I know it's continuous. Now, is it positive? So is this a positive function? That means, is it always above the x-axis? So when you look at this, I'm going to write it back this way. Is that always going to spit out a positive number? Yeah, right? Because remember, you're only plugging in numbers from 1 on to infinity. So you're only plugging in positive numbers. So that's definitely always going to be positive no matter what. And then e raised to any power, of course, is positive. So the ratio of 2 positives is positive. So yeah, we're good. We're always going to have a positive number here, right? So long as we're only looking between 1 and infinity, right? So we got positive. The next thing is to show that it's decreasing. Do you see what I mean? That this is kind of tedious because you've got to do a lot of things before you can actually do the integral. You got to check all this. So how do we show that a function is decreasing? So from Cal 1, we have kind of a nice way of doing this to show that a function is decreasing.
Would we take the derivative and test that?
Yep, we want to show that the derivative of this function is negative. Because when your derivative is negative, your function is decreasing. So I want to show, right, WTS, I want to show that the derivative is negative. If I can show that that's true, then I'm ready. I'm ready to actually run the test. So I need to take the derivative of this. And I think I'm going to just take derivative of that right there. So the derivative of that function should be quotient rule. So derivative of top times bottom minus derivative of bottom times top all over the bottom squared. Now, let's see, let's clean this up. This is just e to the x minus e to the x times x all over e to the x squared. I think I'm going to go one more step. I'm going to factor an e to the x out of the top. 1 minus x over e to the x squared. And I think at this point, I could still simplify. I could cancel one of these e to the x's, but let's just think about this. This is always a positive number, right? This is always a positive number because we're going to take a positive number and square it. So the only real thing for us to consider at this point is, what about this? What can you tell me about that number?
If it's anything higher than 1, it's going to be negative.
Yeah, if it's anything higher than 1, it's going to be negative, right? So if I, and then look, that's where we're looking, right? We're looking from 1 to infinity. Now, at 1, isn't it 0? Like at 1, it's 0. So there is one particular place where this thing is not negative, but everywhere to the right of 1, right, we're going to have a negative derivative. So this should be negative so long as x is bigger than 1. That should be true. So we have decreasing, right? We have decreasing. Any questions?
No, sir.
So, go ahead. So this is negative, right? So check. We have a negative derivative. All right, so that's it. All the conditions are met. So now at this point, we just need to do the improper integral. So I'm going to do the integral from 1 to infinity of the function x. I'm going to write it this way, x e to the negative x dx. And remember that when you do an improper integral, what you have to do is replace infinity with t, and you have to do a limit. So this, we did this back, I don't remember the section offhand, but we've done this. This was a type 1 improper integral. Remember there were 2 types? So this is a type 1. So we really want to do the integral from 1 to t of x e to the negative x dx. But I think it was Alex who said that we've got to do this integration with integration by parts. So I'm going to just do that, do that on the side. Excuse me, I'm going to do the indefinite integral. So I'm not going to put limits of integration. That way we can figure out what the antiderivative is, and then we'll plug it back in over here when we're done. So my integration by parts, I'm going to try and go fast through this, okay? Because we really don't have time to be reviewing this, all right? I'm just going to run through it real quick. dv will be e to the x dx. v will be e to the x, e to the negative x. So this will be negative e to the negative x. So I hope that everyone would be comfortable choosing u to be x, and then dv would be everything else. And then you just fill out your table. And now you do your ultraviolet minus voodoo. Any questions on this while I fill this out?
No.
Okay. So there's our, there's the ultraviolet minus voodoo. And I've got a minus minus, so I'm going to just make that a plus. And now I need that antiderivative, right? I need that antiderivative, and I'm out of room. Okay, so this is going to become negative x e to the negative x. And then when I take the antiderivative of this again, I'm going to get another negative e to the negative x plus some constant. So there's my antiderivative, right? There it is. So now I'm ready to come back over here. I'm going to say limit t goes to infinity. And now the antiderivative, negative x e to the negative x minus e to the negative x. And I want to evaluate that at 1 in t. And then I'm going to plug in t and then subtract what I get when I plug in 1. And just remember the limit's going to just be sitting out here. All right, we're getting close here. So negative t e to the negative t minus e to the negative t. That's what happens when we plug in t, and then we plug in 1, which will give us negative 1 e to the negative 1 minus e to the negative 1. All right. Any questions?
No.
Now what?
We let t go to infinity.
Yeah, let's take the limit now, right? Let's see what happens. And we're actually going to run into a little bit of a problem because of this right here. So before I run the limit, I think it'll be much easier for us to see what's happening here if we just take that e to the negative t and drop it down as e to the t. And then on this one, that becomes negative 2 e to the negative 1. Because these are exactly the same. So I have two of them. I'm just subtracting, right? So I'm just going to put them together. I get that. And let's do our limit. And we're going to run into a little issue. Do y'all see what's happening here? If t goes to infinity, this top goes to negative infinity, and the bottom goes to positive infinity, right? So we would have to do L'Hopital there, wouldn't we? So if we run L'Hopital on that, I'll go ahead and do that next step. I'm going to run L'Hopital on that one. The derivative of the top would be negative 1. The derivative of the bottom would just be itself. And then on this one, I didn't state this, but right here, that one we don't need L'Hopital for, right? Is t goes to infinity. This goes to 1 over infinity, which goes to 0. So this thing's going to go to 0. And then minus becomes plus 2e to the negative 1. And now this one goes, right? This is fixed number over infinity. So that goes to 0 also. So now when we finish it up, we get 0 minus 0 plus 2e to the negative 1. That's really just 2 over e. Any questions? What do we conclude?
That it's convergent at 2 over e.
What is convergent?
The series x e to the negative x.
Okay, so we have to be very careful here because what the test says is that, let me erase this. It says that the original series will converge if the improper integral converges, right? That's what it says. But does this say that it converges to the same thing? It does not, right? So what we've done is we've shown that the improper integral converges to 2 over e, but that does not mean that the series converges to 2 over e. It does mean that the series converges. It just, we don't know what it converges to. And I told you last time that there are only 2 types of series that we are going to be able to find the actual sum of, okay? You remember what they are? The only 2 we can actually find the sum.
Geometric and telescopic.
Yep, those are the only 2, right? And that's if they converge. They don't always converge. The geometric series doesn't have to converge. But if it does, we should be able to find the sum. And the telescopic, if it does converge, we can find the sum. Everything else, we won't be able to find the sum. We will be able to determine if it converges or not. But in this case, our final conclusion is this. So this right here means that the integral of x over e to the x dx, this converges, which implies that the series that we were looking at converges. But that's it. That's the only thing we can say. A lot going on there, yes? A lot going on. I personally don't like the integral test. It just takes forever. Well, it's like, what, 30 minutes? That took us almost. But sometimes that's your only option, is the integral test. All right, we are going to move on. Let's do our next example. And for this one, I'm gonna go really fast, all right? So the next one is this series here. Now, we should all look at that right now, and we should be able to say what it does. All right, we're all comfortable with what type of series that is? Yes, I see you shaking your heads. Harmonic, right? So that's going to diverge. But let's act like we didn't know that. Okay, let's act like we didn't know that, because I told you that, right? I just told you that's what happens, and I tried to prove it to you. But now let's just do it like with an integral test. Because if I rewrite this as f of x equals 1 over x, I have no problem integrating 1 over x, right? You should have no problem integrating 1 over x, right? So I'm not going to do this, but we could check that it's continuous. Okay, it is continuous because the only problem we have is at 0, and we're only looking between 1 and infinity. So it's continuous. It's positive, and it's decreasing. I'm not going to show all that because it'll take too much time. But if we go to the integral, the improper integral, this would become the limit as t goes to infinity of, let's see, let's go ahead and just do the antiderivative of that, which would be the natural log of the absolute value of x, and we're going to evaluate that from 1 to t. So I'm leaving out a lot of steps. I'm trying to show you how we're going to draw a conclusion here, and it'll match up with what we knew before we even started the problem, or when we just started it. So we plug in t, we get natural log of the absolute value of t, and then natural log of 1. I don't need the absolute value here because t is going to be positive, but I'm putting it there anyway. Okay, so as t goes to infinity, the natural log of t, that's going to grow without bound, right? That's going to become infinite. So this thing is going to infinity minus natural log of 1 is 0. So this whole thing is infinite, which means it diverges, right? The integral diverges. And since the integral diverges, so this diverges, that implies that the series we were talking about diverges also. So again, I left out all those other things, showing it's positive and continuous and decreasing. I left that out, but I just wanted to show you that you can actually prove this series diverges using the integral test. In fact, you can generalize this. All right, so let me show you. Can I move off this? Anyone need this still?
Yes, sir, you can move.
Okay. So this generalizes. Let's say we had this, sum n equals 1 to infinity of not just 1 over n, but n raised to some arbitrary power. We'll call it p. So could you do an integral test on this? Turn that into f of x equals 1 over x to some power, and then try and find the antiderivative of that? I would hope that everyone would be comfortable with the idea that that's just x and negative p, and the antiderivative of that would just be power rule, right? So we should be able to handle this. Now, I'm not going to go through all the work, okay? I'm not going to go through it because it will take too much time. But we get a very nice conclusion, all right? And that is on your formula sheets. Oh, wrong thing here. It's right here, it's called a P series, okay? And P series are awesome because you don't have to do anything. All you have to do is look at them. So this says that if you have a series, right, where it's 1 over n to a power. So the thing that's changing, the n is in the base, right? And the power p is fixed. Then you can automatically determine convergence or divergence just by knowing what the value of p is. If p is greater than 1, it's going to converge. And if p is less than or equal to 1, it's going to diverge. All right, so that's now something in our arsenal. Let's just apply that to some quick examples. Students love the P series because there's nothing to do. So if I gave you this one, does this converge or diverge? Let's do sum n equals 1 to infinity of 1 over n to the 3rd power. Let's see, who have I not called on lately? Jorge? Is Jorge here? I see you, Jorge. You there?
Yes, sir.
Yep. Okay, so I didn't leave that note up for you, but do you see that this is a p-series?
Yes, sir.
Okay, so it's a p-series. What's the value of p?
3.
3, okay, and you're checking now, is that bigger than 1 or less than or equal to 1, right? So this is bigger than 1. And if it's bigger than 1, do you remember what the formula said?
No, I don't.
Okay, so anyone else?
It'll converge.
It'll converge. Okay, so this is a p-series with the p being 3, which is bigger than 1. Therefore, that series converges. You don't have to show anything, okay? You don't have to show anything. You just have to make it clear that you know it's a p-series and that the p-value is bigger than 1, all right? How about this one? Converge or diverge? Sum n equals 1 to infinity, 1 over the cube root, or yeah, we'll do cube root of n.
Diverge.
Diverge. Okay, so why is that divergent, Varun?
1/3 is less than 1.
Yeah, so Varun is realizing that that's really just what, n to the 1/3 power, right? So it's a p-series with p being 1/3, which is less than 1 or less than or equal to 1. And anytime you have that, you have divergence. So it diverges. Oh, I forgot to put that this converged. Sorry, converged. That converges. So if you're taking a test or something and you get a problem like this, you would just simply state, you know, p series, p is bigger than 1, and therefore it converges. And that's it. Nothing else to do. Okay, let's look at another one. How about this one? How about this? Converge or diverge? 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus a half plus 1 over the square root of 5 plus dot, dot, dot. So this is the first time that I've given you the series written out as a sum instead of giving you the sigma notation, right? So it may not be obvious at this point that this is a p-series, but we would need to convert it to its sigma notation. So this is where you'd have to go back to like what we did in 8.1. You'd have to figure out what's going on here, right? So does anyone see it?
Is a to the n equal to 1 over the square root of n?
1 over the square root of n. That's it, right? Check that for yourself. You plug in 1, you get this. Plug in 2, you get that. 3, you get that. When you plug in 4, you actually do the square root of 4, which gives you 2. So that's why that one looks a little off, but everything else follows the pattern. And then once you see that, you should be able to determine its p-series, p being a half, which is less than or equal to 1. Therefore, we have divergence. Okay. Any questions?
No.
Okay.
Series always going to be rational,
Will it always be rational? What do you mean rational?
as in like it'll always be like 1 over n.
Well, you could have any constant up there. You could have like 4 over n or 10 over n or something like that.
Okay.
Yeah, but a general p-series. So if we had a constant on top, that would not impact anything. You know, if you change this to, let's say 5, and that would be 5 here, 5 here, 5 here, 5 here, that would still diverge. Not sure if that's what you're asking.
What if it's not in a fractional form?
How do you mean not in a fractional form?
Like 5 times n, or I don't know.
Okay, so, all right, so what if you had this? What if you had, I don't know, you just said 5n, right?
Yeah, to a power, I guess.
Or you want n squared? Something like that?
So yeah, something like that.
Okay, so why don't y'all tell me?
I
Well, that
mean,
would converge,
you
right?
can still make it a p-series because in that sense it would be 5 over n to the negative 2, which is less than or equal to 1, so it would diverge.
Yeah, you could look at it as a p-series
Yeah.
written that way. You could. Now, why not? But you could also just do the pregnancy test, right? What's the limit of that as you go to infinity?
10n.
Infinity,
Oh.
right? And that's not 0. So this would actually, the nth term test, right, would allow you to draw a conclusion. The conclusion would be it diverges, which matches exactly what the p-series would be telling you, because your p would be -2, which would be less than or equal to 1, which would diverge. So there, you could look at it from 2 different lenses there, I guess, if you wanted to.
Okay.
Does that address your question?
Yes, yes, sir.
Okay. All right, so now we're ready to move on to the next test. It's called the comparison test. And this always causes some issues, all right? So I'm going to try and illustrate the test first. Before we look at it, I'm trying to illustrate it with an animation here. All right, I thought a lot about whether or not I wanted to give you this or not. Okay. So remember when I first started showing you these animations, the box on the left here is the sequence. It's just the dots, right, that come off the sequence. And then the box on the right is the sum of the numbers within a sequence, right? So what we would do is we would just drag this out. We would start looking at the sequence, and then this adds them up, and we try and see what this is going towards, right? So I want you to just consider this. Let's say that we are given, okay, we're given this series, right? This is given to us, all right? Now, in our picture, that's the black dots. I should have done that in black, but these are our black dots, all right? Say we're given that. And then what if I tell you that there's another series, okay? There's another series, this one, which is the red dots. Okay, so y'all see there's some black dots here, and you see there's some red dots. So you're given some series, and then I'm telling you that there's another series that's red where this is true. What does that mean? Graphically here in this picture, what does it mean? If I tell you that this other series that I'm looking at, the b sub n is greater than, I'll even say greater than or equal. What does this mean? This sequence is always bigger than that sequence, right? So in the
Right.
picture, the red dots are always above the black dots, right? Yes?
Yes, sir.
Now, what if I also tell you that this other series right here converges? What can you tell me about this series then? So think about what's happening here. The red dots are always bigger than the black dots, right? So, and I'm also telling you that that this series converges, which means when I add up those red dots, it goes to a number, right? So watch, as I start to add this up, as I start to add these up, look at what happens on the right-hand side. You see that the red dots represent what the red series is doing? And do y'all notice that the black over here is always below it? Well, why is it below it? Because all the black dots are smaller than the red dots, right? So when I add these up, whatever, all these black ones should add up to be something less than all the red ones, right? Does that make logical sense to you? So that is what this comparison test is going to allow us to do. It's going to say, hey, look, if you have some series that's given to you, okay? If you have that given to you, so I'm going to provide you a problem and say, hey, does this converge or diverge? You are going to compare that series to another series. And that other series right here, you get to pick it. You get to pick it. But the thing is, you need to know what that series does. The one that you pick, you need to know what it does. And then you have to show that this inequality is true. And if that inequality is true, then if your original series converges, then so does the one if the one you're comparing it to converges, then so does the original one. Okay, we'll run through an example, all right? I hope that you see that, the logic behind that. Now, what if we have this though? Okay, so what about this scenario? What if you have a series that's given, and you have another series that you come up with where the inequality is the other way around. Okay, that means that the black dots are always bigger than the red dots, always taller, right? Bigger values. Then if that converges, can you say anything about that anymore? Like, let's say that this series converges to a number. Can you say that that converges? I see some heads no. Why not? Can someone explain that? If all the red dots,
Because the one above could increase.
exactly. So the one that's in red, right? The one that's in red, we know that that converges when you add them up. But all the black dots are bigger. So since they're bigger, they could converge when you add them up, but it could also take off to infinity. So this actually, the only way this would work is if we could say that this series, what? Diverged. If this series that we compare it to diverges, and this inequality is true, it means that when I add things up, the black dots are always bigger than the red. So when I add them up, the sum of the black is going to be bigger than the sum of the red, but the sum of the red is going to infinity. So watch what happens. Start adding these up. Remember, the black dots are bigger than the red. So you can see on the right-hand side, you see how that the red dots are diverging here? They're going up. And if the black dots were always bigger than the red, then that sum should also stay above the red dots on the right-hand side. So it's a little tricky. And I think that once we get through a few examples, hopefully it'll make a little more sense. Let's look at the actual rule. Are there any questions right at this moment about it? Okay, there's your P series. Here it is. Okay, so here's the test. This is on your formula sheets. Okay, we are going to be focusing all of our attention on just the first two parts of this. So there's a couple of things that we have to be clear on. You're going to be dealing with a series, okay? This is given, okay? That's given to you. This is the thing that you're going to compare it to. And you, that's you, must determine this. And you'll see how we'll do it in a second. I'll give you, there's some thought that goes into this. Now, we also have some other restrictions when you use a comparison test. The sequences, both of them, the thing that's given to you and the one that you're comparing to, they must contain positive numbers only. So this will not work if your series has alternating or negatives in it. This won't work, but don't worry, we have a test for that. So we'll deal with that when we get to it. So as long as we're dealing with the sum of positive numbers, then here are the conclusions from the comparison test. If the thing that you're comparing it to, right? If the thing you're comparing to converges and the A sub n is smaller than the B sub n, then the original series converges. So again, that's just saying that all the little guys in this series are smaller than all the other guys in this series. So if all these add up to be a number, then this must add up to be a number. And then part two says it the other way around. If this series diverges, becomes infinite, and all of these A sub n's are bigger than all these B sub n's, and you add these up, then that should be bigger than whatever this sum is, so it should be infinite also. All right. Like I said when I started this, I know that this is always a little confusing for students first time they see it, so let's just do an example, right? Let's just do an example and see how this is all going to play out. Let me erase all this. Okay, so your first example, does this converge or diverge? Sum n equals 1 to infinity, 1 over 3 to the n plus n. Nth term test, right? Pregnancy test fails. I'm not going to write it down. That goes to 0, doesn't it? The sequence Goes to 0. Okay. Is it geometric? I mean, kind of, right? But then you have that plus n down there, which makes it not geometric. But it does, I mean, like that n wasn't there. If this n wasn't there, it would be geometric, wouldn't it? Okay. Right. Well, it's not geometric. It's not harmonic. It's not linear over, I mean, sorry, constant over linear. It's not telescopic because we can't do partial fractions. Integral test. You want to integrate that? No, thank you. In fact, look, let's integrate this on Wolfram alpha. All right. Watch this. This is going to be pretty cool. Let's just try and find, let's integrate integral of, what was it? 1/3 raised to the x plus x. All right, here we go. Look at the answer. The antiderivative of 1/3 to the x plus x. So this is if we wanted to do the integral test, right? We'd have to convert it to a function of x and be able to find the antiderivative. Look what it says. No result found in terms of standard mathematical functions. That means Wolfram alpha can't integrate that. Now, that Wolfram alpha actually does do the integral here, but this right here is the answer. But look what it's calling it. The series expansion. Well, guess what? That's where we're headed, okay? We are headed to this. That's why we're studying series. It's because in general, integration can be very difficult to do, but we do have ways of doing things using series. So we'll actually, well, we're not gonna do this problem, but we will see that it will be possible to do integrals that normally, traditionally can't be done by hand. We convert things over to their series and then we can do them with relative ease, all right? So we don't want integral tests, okay? It's not a p series, right? This is not like 1/n to the p. So the only other thing we have now is this comparison test. So this is now where you have to come up with something that you want to compare it to. So when you look at that, here's the thing I'm going to compare it to. So I'm going to do a comparison test. Does anybody just have a gut instinct as to something that this kind of looks like that you want to compare it to, but you better know what it does? Like what you're comparing it to, you better be able to tell me if it converges or diverges. So anyone want to throw a guess out here?
1/n.
Okay, 1/n. So what you're saying is, all right, well, look, I mean, if I ignore the 3 to the n, then this looks a lot like 1/n, right? And this right here, I know diverges. Do y'all agree we could do that? We could try that? Okay, does someone have another sort of thing they might want to try?
1/3 to the n.
Okay, 1/3 to the n. All right, now what type of series would this be?
P series.
Careful, the n's in the wrong place. If you switch them, right?
For it to be geometric, does the exponent have to be n-1?
We could always make it n-1, couldn't we? Couldn't we massage this? We could massage this, couldn't we? Like we could look at this as 1/3 to the n, right? And then what we could do is make that -1 + 1. We could do that, right? So just by this step right here, don't we know this is geometric? So this is geometric. And the r here is 1/3. And that's less than 1, and that means it converges. So I'm moving kind of quickly through that, but we've talked about geometric series already. If you have a geometric series, which we do, and we can identify what r is, which we can, then as long as that r is less than 1, we have convergence, right? This is perfect. I couldn't have planned this better because one student picked this one, which diverged, and another student picked this one, which converged. We're going to do them both, okay? We're going to do them both. You ready? Let's start with this first one. Let's see if this will work. Okay, we'll come back to that. We'll do that one on the next step. So here's what we want to do. We want to take this series and we want to compare it to that series. We know that that series diverges. All right. So now what I need to do is I want to show, now this is where you go up to the formula. So we had a series and we are comparing it to something that diverges. So we are doing this right here, right? The series that we picked diverges. So what we need to show then is this. If we can show what's in blue is true, then whatever this series does, that one also does the same thing. But we have to be able to show that all of these guys here always remain bigger than all of these guys here. Because this sum, this adds up to be infinity, we want to draw a conclusion that this is infinite, which means that that sequence has to be bigger than that sequence. Let's see if we can show it. Any questions? I want to show that this is true. Are there any questions why I'm showing that? Or are there any questions why the inequality is pointed that way and not the other way?
No, sir.
All right, so now at this point, we would clear fractions out, right? So I would get n greater than or equal to 3 to the n plus n. And remember, we don't have to worry about flipping the inequality over because we know we're not multiplying both sides by a negative because n is always positive here. So we're just going to stick with the inequality this way. I know that I don't like saying cross multiply, right? We're not, I mean, we're clearing fractions technically, but students just love to always look at that as cross multiplying. So we'll say that. Is this true? Is that true?
No.
No, subtract n on both sides. And you get 0 is bigger than or equal to 3 to the n. And that is not true, right? 3 raised to any power is going to be a positive number. This is not true. Okay. Very, very important right now. What is our conclusion?
That the series converges?
So I think your logic there, Christian, is this. We did the comparison test with something that diverged, right?
Yeah.
We tried to show that this inequality was true, but we said it wasn't. So I think most students would say, okay, then this didn't work. That means that must converge. No, this means the test failed. It means that it's like a pregnancy test again. It's a test that's inconclusive. You don't know what happens. And that means that our choice of this as our comparison was not good enough to draw a conclusion. All right, now rest assured we will be able to do it. So test fails. Now let me explain why the other one will work. Okay, so the other one that I scratched out, we're gonna do that one now. Let me explain why this is the one we should have gone with to start. When you think about n, right? N is going to start at 1 and it's going to go to infinity. When n is really, really big, right? When n starts to get huge, which of these two pieces is more dominant? N or 3 to the n?
3 to the n.
3 to the n. That's exponential. That is the dominant term in that denominator. And so it's almost like we're saying for big enough values of n, this is kind of insignificant. You know, think about if that's like 3 to the 1 million. That number is so huge that adding a million to it still would be insignificant compared to 3 raised to the million power, right? So that is kind of what should have led us down this road. But I'm glad we went down this road because I wanted you to see why this wouldn't work. In fact, I was going to do that regardless if anyone said anything. I was going to do this anyway. I was just going to do it second. All right. So let's go with the other one now. I'm going to start over. Here's the original problem. I'm going to compare this to sum n equals 1 to infinity, 1 over 3 to the n. And we know that this is convergent because it's a geometric, right? You, by the way, you do not have to figure out what this converges to. So you don't have to go and make it the n minus 1 plus 1 and all. You don't need to do that because all you need to know is that it converges. If that converges, this one over here will converge, but we won't know what it converges to. We just know it converges. All right. So here we go. Let me grab this. I'll put this right under here. Okay, so what we're doing now is we have something we're comparing to, but the thing we're comparing to converges, right? So this is what we're looking at. It converges, right? The thing we're comparing to converges. So we need to show that this inequality is true. That all of these guys always remain smaller than all of these guys. And as long as we can show that, we're in business. So I want to show that A sub n is less than B sub n. And A sub n here is the sequence on the first series, and B sub n is the sequence on the second series. And if you do a similar, kind of cross multiply thing, now you can get rid of the 3 to the n's by subtracting it on both sides. And you get that statement, which is true. N is bigger than 0. Any questions on that algebra?
No, sir.
Okay. Therefore, by the comparison test, the original series does what?
Converges.
Converges. What do you think?
I just need more practice, I guess.
Yeah, of course. I mean, you can see how this can become problematic because you're the one who has to determine what to compare it to, right? And
Right.
so, that's going to take a little bit of, a lot of practice for you to get to a point where you can look at something that's given to you and be like, oh, you know what? I feel good that I should compare it to this, right? I mean, that's going to take a little bit of work because it's not going to be like, this step 1, step 2, step 3. You've got to think about it, right? All right, let's do another one. Which is the one I want to do now? Oh, yeah. This one. Okay, I'm trying to get 2 more in here today. Okay, we're going to do a little Jeopardy here. So I'll give you a couple of minutes. Let me give you 3 minutes, and I just want you to think through this. And don't box yourself in. Look at this as a brand new series. Go through the little Rolodex of things to do. Make sure you're convinced we should do a comparison. And if you want to, then, oh, you know what? Hold on. I need to start the series at 2. Sorry. I need to start at 2. Almost forgot. Do y'all see why? If I let n be 1, this is
You'd get 1/0. That's
Yeah,
undefined.
it's okay to start it at 2. It's just one less number in the series, but that's no big deal. It goes on forever. So let's do our little 3-minute break here. Not break for you to think.
I was gonna ask that question too.
Whether or not we should do an integral test?
Yeah, because I worked it out and I was actually able to find out that it's not that bad to take the integration of it.
Yeah, I agree. I'm not going to do it though, but yes, it would. It could potentially, the integral test could be something that we use here. So end term doesn't work. Limit of that, infinity over infinity. L'Hopital, it's going to go to 0. It's not geometric. It's not harmonic. It's not telescopic. Oh, I forgot P series. It's not a P series. Integral test, maybe. Did anybody come up with something to compare it to though?
You could do 1 over n.
Okay, so why? Why did you choose 1 over n?
I mean, I don't know if this like checks out, but it in a sense it's very similar to 1 over n. Just because if you like divide n over 3 by n over 4, you get like a 1 over n kind of thing. It's just n minus 1 at the bottom.
Yeah, I agree. That's the way I think you should try and look at this.
Okay, cool.
That minus 1 right there is really insignificant when n gets big, right? And so that really kind of looks like just n cubed over n to the 4th, which is like 1 over n. I think it's worth a try. I need to fix something. I need to start my sum here at 2, just because my original one started at 2. But this is still going to be harmonic, right? And still diverges. Okay, so if that's the case, if that's what you want to compare it to, Ross, that was you, right?
Yes, sir.
Okay, then what do you need to show, Ross, in order for you to draw any conclusion here?
I don't remember the notes, but I think we need to show that it's greater than, or is
Yes.
it less than?
It's greater.
Oh, cool.
Good.
We need to
Now,
show that it's greater than 1 over n.
yeah, because think about it, Ross. You know that these are blowing up, right? You know that the thing you picked, 1 over n, is blowing up. These are getting bigger. I mean, not the sun's getting bigger. So, that means that you want to show that these are always bigger than those, because then that'll force those to blow up also. Yeah. Okay. So let's see. Let's see if, and then, you know, for everyone, this is all we're doing here. We're looking at this and we're taking this one right here. We've picked something that diverges, so we have to show that that inequality is true. All right, let's show. Is it true? Is n cubed over n to the 4th minus 1 bigger than or equal to 1 over n? So do a little like cross multiply type thing here. All right, multiply, and we get, subtract the n to the 4th on both sides, you get 0 is bigger than or equal to -1. That's true as of today, that's still true. So, yes. That's it. Diverged. Therefore, the original series diverges. Good. Any questions? So Varun, you had talked about doing the integral test. I think the integral test would have worked, but you still would have had to have shown it's positive, decreasing, all those things. That would have taken some time. This, once we have that, it's just showing this inequality. And once we do that, we're done. All right, I'm gonna give you another problem. I'll give you a few minutes. This is not a trick question, but you're going to run into a problem. What do y'all want to compare it to?
We can't do 1 over n because it's not gonna, it's gonna be greater than or less than.
So you tried 1 over n though, right? Because you could use the same logic we just had a second ago, that the 1 really doesn't matter. This really looks like n cubed over n to the 4th, which is really like 1 over n, right?
Mhm.
Okay, so you do that, this diverges, and now you need to show, I want everyone to write this down because this is going to be real important to understand how we're going to get this. So we're comparing it to this, so we want to show that that one's bigger than that one or equal to. So we go here. This is what we need to show. We cross multiply. And then we subtract n to the 4th on both sides, and we get that, which is not true. Which means the test fails, right? Which means that our choice of the thing to compare it to didn't work, right? Any questions up to this point?
No, sir.
Okay, so here's where things get a little weird. So I'm looking at this, I'm like, man, you know, come on, this has got to be divergent. I mean, it looks so much like 1 over n. So I'm looking back at my work right now, and I'm thinking, how did that get messed up? It got messed up because I had a +1 here, right? In the previous problem, I had a -1 there. So maybe there's a way that I could fix this, just make a small little tweak.
Could we make it 1 over n plus 1 that we compare it to? Would that
You
do anything?
you could do something like that, 1 over n plus 1, which would be harmonic, right?
Yeah, because then it would equal, like it would be n to the 4th plus 1 is greater than or equal to n to the 4th plus 1.
Okay, so yeah, let me do it this way. I'm going to go with that because you mentioned it, Ross. So Ross is saying, why don't we do n plus 1 here instead? Now, I think what Ross is seeing is that if we do that, it's still harmonic, right? Constant over linear, it's still divergent. But then we have an n plus 1 down here, right? And then when we cross multiply, we get, on this side, we don't get n to the 4th, we get n to the 4th plus n cubed, right? When we do this one times this one. Y'all see that? And then when you subtract on both sides, yes, these go away, but now you have n cubed is greater than or equal to 1. And that is true. Does that make sense? Just a slight little tweak there worked. Good. Now I want to show you how I would have done it. That's fine. I mean, what you did is fine. That's perfectly great, actually. But let's go back to the original problem. It was n cubed over n to the 4th plus 1. And then we compared it to 1 over n. We cross multiplied. We subtracted and we got 0 bigger than or equal to 1, and that wasn't true. So what I was saying was this +1 here is causing the issue, right? So what if I made, is there a way I could have made the left side 2n to the 4th? Think about that. If this would have been 2n to the 4th instead, then when I subtracted n to the 4th on both sides, what would I have gotten? N to the 4th bigger than or equal to 1, which would have been true, right? So is there a way I could have made this side 2 n to the 4th? Well, where did it come from? It came from multiplying those together, right? So can you make that a 2n to the 4th? Sure, put a 2 right there. Put a 2 right there next to the n, which means go back up here and change that to 1 over 2n, which is still harmonic, right? So this is like me kind of reverse engineering so first we do this and we say, oh crap, or sorry, it's right here. We say, oh no, 0 is not bigger than 1. Then we say, oh, if we kind of tweak it a little bit, then we can get it to work. Weird, huh? So sometimes you actually have to run the test and have it not succeed for you to be able to figure out how to make it succeed, which just adds another layer to the complexity of this sort of thing. All right, let's do another one. How are we doing on time? Oh, I'm doing good on time today. That one's a little too. You know what? I think we're good. I think you'll understand. Y'all just have to get your hands dirty in the homework. All right. Now, when we were looking at the comparison test, come on. We were looking at this. We were looking at what we've done so far is we've done this. We've seen what happens if we compare it to something that's converging, and then here we compare it to something that's diverging. We've addressed those two. There's a third part to the comparison test, which in my opinion should almost be its own little thing. This should be almost its own test. What's in blue is another way you can run a comparison test where you don't have to do any inequalities at all. You know how we've been having to show this inequality is true? So what it says, everything is this exactly the same. You start with something, you have to come up with something to compare it to, but instead of trying to show that these inequalities are true, all you have to do is take the limit as n goes to infinity of the ratio of the sequences. And if that turns out to be a number, so this has to turn into a positive real number, it can't be infinity. If it turns out to be a number, then whatever one series does, they both do. Okay, so let me show you this in action. Let's take the problem we just did. Okay, we compared that to 1 over n. Actually, we compared it, well, let's go with 1 over n. Okay, let's go with 1 over n. And start at 2. That's what we had done initially, right? We said, hey, this worked. But when we tried to do it with this, the inequality did not hold. Do y'all agree? The inequality was not true. But let's do this blue one instead. So all you have to do now is take the limit as n goes to infinity of this sequence, that's a sub n, over the other one, 1 over n, and hope that that turns out to be a positive number. So I'm just going to do a little algebra here. I'm going to flip this n on the bottom up. It's going to join that one, so it's become n to the 4th over n to the 4th plus 1. And that's infinity over infinity. But if I do L'Hopital on that, if I do L'Hopital one time, I get 4n to the 3rd over 4n to the 3rd, and that's 1. And guess what? 1 is a positive constant, right? And since I got a positive constant as an answer, both series either converge or they both diverge. Well, I already know one of them diverges, right? Which means they both have to diverge. So our conclusion is that this diverges. Bam, what do you think about that? Isn't that one nice?
Yeah, that was pretty cool.
Yeah, that because 1 over n did not work for us when we tried using this version. But when we use the third version of this, it does work, which is weird, but it does. So this is sometimes referred to as the limit comparison test. Now, in this book, they throw it in, or we're throwing it in with the comparison test, but this specific one is called the limit comparison. If we go back and we look at the example that we did let me see, when we first started a comparison, we look at this one. Let's do this one. Let's see, could we get this one with the limit comparison? I don't want you to get married to the limit comparison test, all right? It's a great test. It works a lot, but it's not always the best thing. So let's do this one. So we're trying to figure out this converges or diverges. We already did this problem. We showed it converged. We did. Let's compare it to this geometric series, which is what we did earlier. And we know that that converges. But instead of trying to figure out the inequality, let's take the limit as n goes to infinity of the first one divided by the second one, the one we're comparing. Let's do a little algebra. Flipping 3 to the n on top, 3 to the n plus n on the bottom. And if we let n go to infinity here, we're going to get infinity over infinity, right? So we've got to do L'Hopital. So we do L'Hopital. And now you have to go back to college algebra and remember what the derivative of 3 to the n is. So in case you've forgotten, the derivative of a to the x is a to the x times natural log of a. That's from Cal 1. So if we're going to take derivative of 3 to the n, we should get itself 3 to the n times natural log of 3 over, now the derivative of the bottom, we do these separately. We get 3 to the n times natural log of 3 plus 1. You all okay with that?
Yes, sir.
Okay, we still have infinity over infinity. So we got to do L'Hopital again. Now keep in mind that this natural log of 3, that is just a constant, right? So it's just going to come for the ride. We don't need to do product rule or anything. So when I take the derivative of the 3 to the n again, I'm going to get 3 to the n times natural log of 3, but I already had a natural log of 3 there. And on the bottom, I get 3 to the n times natural log of 3, but I already had a natural log of 3 there. But this time the derivative of the 1 is 0. So we just get this, right? And that's just 1. Everything cancels out. And 1 is a positive constant. And because 1 is a positive constant, whatever 1 does, they both do. So we can conclude that this must also converge. Do y'all like that test?
Oh yeah, pretty straightforward.
Yeah, it's pretty nice as long as your limits work out. Okay, so I showed you that we could do that test for this problem. I won't do it, but this is the problem we did before where I had a minus instead of a plus. Limit comparison would have worked for this one too. The problem we did before that, okay, we just did that one. Limit comparison worked. What about this one? What about, where the hell is it? What about this problem that we did with the integral test? Remember this? I wonder if we could do this one with the limit comparison. Maybe. Let's try it. So does this converge or diverge?
Converges.
Well, we know it converges from the integral test, right? But let's act like we didn't know that. I'm going to rewrite this as sum n over e to the n. Okay, what would you compare that to? Someone want to tell me what they would compare that to? Got to go with something.
Maybe 1 over e to the x.
Yeah, I like 1 over e to the n. I like that because that n on top, even though it does get big, e to the n dominates, right? So we're going to kind of act like that n's not there. I don't know if this could work, but I do know that this is geometric. And I do know that it converges. Why do I know that? Because that can be written as 1 over e to the n. And 1 over e is smaller than 1, right? That number is smaller than 1. So this should be a convergent geometric series. Now, going to run the limit comparison. So I'm going to take the limit as n goes to infinity of the first one, n over e to the n, over the second one, 1 over e to the n. And then when I do that, limit n goes to infinity, I flip, and don't the e to the n's go away? The e to the n's cancel, and all you're left with is n. And what does n go to infinity? As n goes to infinity, what does n do? Goes to infinity. Is infinity a positive constant? No, it has to. Infinity is an idea, right? It's an idea of a number that just gets bigger and bigger. In order for the limit comparison test to work, you have to get a positive number, a fixed positive number. And that means this test fails. And so it was looking really good that the limit comparison was going to come save us from everything, right? But it doesn't always work. So I don't know if that's good news or what, or bad news, or it's just news at this point, okay?
Are there so many tests because like each one of them doesn't like has like their own flaws depending on certain series?
Absolutely. Absolutely. Each test has strengths and weaknesses, and you have multiple tests to compensate for where one test might not be doable. And we still have more tests, right? We're not done yet. We have, if you look at this, we've got our n-term test, we've got that. Geometric, we kind of got. P-series, we've got the integral test, great. Comparison test, got it. That includes the limit comparison. We still have not talked about the almighty ratio test, the root test, alternating series test, and then this right here, which is just something I'll show you next time. The almighty ratio test. This right here is the big daddy right here. That's the one right there that just kind of, that's the most powerful test we have right there. And we use it the most. Just we're not there yet, okay? That'll be next class. So we're getting there, right? We're kind of getting through this a little bit at a time here, aren't we? I think one of the challenges will be on the next exam, on the final, will be I present you with the series, ask you if it converges or diverges, and then you don't know what test to use, right? So it's not going to be like, oh, use the integral test to show this converges, or use the comparison test to show this, you know, it's going to be, here it is, converge or diverge, use what you know. And you have to figure it out. You have to figure it out. So that's where the practice and the homework and everything else, that's where that becomes useful. Let me see if there's anything here.
Professor, is it safe to say that the limit comparison test works for everything but something that's raised like e to the n or something like that?
I'm not going to say that. I'm sure that there are some other situations where you could have something that's not what you're suggesting and it wouldn't work. Yeah. Now, each of these tests do have little little hints next to them, you know, like the comparison series is often a geometric series or a P series. You know, so they do give you little hints and tips over here as to like maybe when you want to use them, but like this one right here, P series, useful for the comparison test if the n term is similar to 1 over n to the p. But there's nothing hard concrete that says use this every time you see this, right? It's just kind of like hints or comments is what they call them here.
Can we use this formula sheet on our next exam?
Yes. You're welcome.
Yeah, I really do appreciate that.
I couldn't use this. This wasn't allowed on my calculus test when I was a student. We had to know all of this. Yeah. But I'm not a fan of that. And that's because I'm not a person who memorizes things well. I can think logically and I can process information, but I'm not a memorizer, you know? And so I always think that in the real world, you're never going to be like locked in a room without references. So I'd rather you be able to use reference that's more practical than to you prove to me that you can memorize a formula sheet that you'll never, ever have to memorize ever again, you know? Now, once you do enough of these, you kind of get it, you know, like after you've done enough, you're like, okay, yeah, I know limit comparison. I know how to do that. So after you kind of suffered enough, you'll find yourself not looking at the sheet as much, but it'll be there for you. Okay, so I have a little bit of time. I don't have enough time to start the next section. I want us to look at something kind of, we're on topic, but kind of weird. All right, so I want you to consider this series. Sum n equals 1 to infinity, -1 to the n. Let's just start writing it out. What is this?
-1, 1, -1, 1.
Plus, so we're doing the series this time, right? So it's -1 plus 1, -1 plus 1, -1 plus 1, right? Do you agree? It goes forever. Now, this is an alternating series, right? It's an alternating series. We have not looked at anything like this because everything we pretty much have looked at has required that we don't have switching of signs. If you go back and look at your formula sheet, almost everything we've looked at, I always do that. So everything we've looked at, geometric series, that one can't alternate, but 1 over n to the p will never have a negative in it. The integral test requires that the function be positive, so we can only use that for positive series. Comparison tests require that the series are positive. We have not up to this point dealt with anything where we have negative parts to our series, right? Okay, so since we've done, this is getting us into new territory. All right, I don't know if this converges or not. Well, I do, but I want you to act like you don't know whether or not this converges or diverges. Okay, does anyone have an idea of what they would think whether or not this would converge or diverge?
I would think that it would converge, but to like 2 different values, because when n is positive, the value would be, you know, just 1, and then if it's an odd number, it would be -1.
Yeah, so like if you look at, let's get rid of all that in blue. So if you just look at the first number, it's going to be -1, right? Okay, and then, so if we're looking at partial sums, like S sub 1 would be just the first one. S sub 2 would be the first 2 added. The first 2 added would be what? The first 2 here?
Yeah.
0. Okay, and then now S sub 3 would be what? The first 3 added, which would be back to -1, and then 0, and then back to -1, right? So if you keep on doing this, is that converging to one number? So Christian's saying it's going to 2 places. I agree with that. It's going 2 different places. But to be convergent, you have to go to one number. So does it not appear that this is divergent then? Going 2 places? It appears that way. But I want you to just think about this. See if this blows your mind at all. Okay, so I'm gonna write what S is. S I'm gonna define to be this sum. Okay, and then I'm gonna write S again below it. But what I'm gonna do is I'm gonna put 0 -1 plus 1 -1 plus 1 -1 plus 1 minus ... So all I did was added a 0 to the front of it. Isn't that the same thing? Yeah? Okay, now what I'd like for you to do is I'd like for you to add these straight down. So what happens if you add those down? S plus S would give you 2 S's. And now just start adding down. What do you get? This is -1, and then these 2 added down.
0.
0, 0, 0, 0, 0, 0. So you wind up getting 2 S's equal to -1, right? So that means that S would be -1 over 2, just divide both sides by 2. So the sum is -1/2. What? Does that number make sense though? Because when Christian said it's going to two different numbers, what were the two numbers that it were going to? 0 and -1. What does this answer appear to be headed towards?
-1/2.
Right in the middle of those two, right? So the answer does seem somewhat logical, doesn't it? Like
Yeah, it
somewhat
does.
logical. Okay. That's weird. It's weird though, right? Now, please do not take this as I'm telling you that, I'm not telling you that this converges to -1/2. I'm not telling you that. I'm just saying if I mess with the algebra like this, I can maybe convince you that it does, right? Okay, I want you to look at another one. How about this? How about sum n equals 1 to infinity of n? This is equal to, let's see, you plug in, you get 1 plus 2 plus 3 plus 4 plus ... right, forever? Do y'all think that that converges or diverges?
It diverges because it gets infinitely big.
It's infinitely big. Does everyone, I mean, that should make perfect sense, or not perfect sense, but that should make some sense, yes? Give me a second, I need to look up something. I haven't done this one in a while. Let's see if I have it in my notes. I might have to wing it. Yeah, let me wing it. Let me see if I can wing it. What are we doing on time? Oh, I'm out of time. Shit. Okay. I'll pick up with that next time. I'm going to show you, I'm trying to convince you that this does not add up to be infinity. We'll see. We'll see if I can. We'll pick up with that next time. For you, what you need to do for next class on Monday is attempt to do, the homework for 8.3. That's integral test and comparison test. That's all that section covers. So use my homework solution videos to help you out, but make sure you get through all those. And yeah, that's pretty much all I've got for you. I did show my other class I did show them my test. Why is it not coming up? Maybe you all would be interested. You can leave if you want, but I showed my other class my final from last spring. So just to give you an idea of the type of questions and number of questions. So there were 10 questions and 2 bonuses on the final exam. So the first problem I asked, and remember, this is just to give you an idea of like what I've done in the past. There's no indication of what you're going to get, but I asked them to rewrite this repeating decimal as a fraction. We've done that. That means you have to rewrite this and then look at it as a geometric series. And this one right here, find the sum. Collapsing. This is a collapsing series, telescopic. So you got to find the pattern, get the cancellation to happen, figure out what happens. This one, you take this series, you rewrite it in sigma notation. So you have to find the formula for it first. And then once you have the formula, convince me that it diverges or converges, which means you have to run a test, right? So I asked that. And then after number 3, there's nothing else here that you can do at this point. So yeah, all right. So have a good weekend, right? It's Wednesday. Yeah.
Yes,
so
sir.
have a good weekend, do your homework, and I'll be getting those tests graded hopefully pretty soon.
All right. You'll be there in your office hours?
I will. 1 o'clock, right?
Right.
1 to 2. Yep.
All right. I'll probably be there a little late, but I'll be there.
Yep. All right.
Thank you.
See you.
Thanks, Professor.
All right. Have a good one.
You too.